In this video, we're going to talk about rational equations. Before we begin, we need to talk about the domain of a rational expression or a rational equation. The domain is defined as the values of the variable that the variable can assume in an expression. So when we're talking about rational equations, they contain some sort of rational expression. That means that you'll have a variable in a denominator. We want to make sure that the value that that variable does not make that denominator zero. If a denominator is zero, that expression is undefined, and if our equation has any undefined expression, the entire equation is undefined as well. So we're looking for the domain, which we'll start with all the real numbers, and then we'll exclude any values that make the expression undefined. So this is the process that we use to find the domain of a rational expression. So in the example you see here, we have the expression 5 minus x divided by x plus 1. So if we think about the denominator, we're looking for the value of the variable x that would make this denominator 0. So the only value here that would make this 0 would be a -1. But any other value of x we could put in, and we could simplify that expression and get some other real number. So the domain would be all real values except for -1. -1 is the only value that would make that expression undefined. So we're going to use the domain as part of our check process when we're solving rational equations, because we want to make sure that whatever solutions we get will satisfy the domain. So here's your definition for a rational equation. A rational equation is any equation that involves a rational expression. You'll be able to recognize rational equations because you'll have variables in the denominator. When we're solving rational equations, we are going to use a similar process as what we've done before when we had equations with fractions. We're going to clear out the denominators. The equation that you get after you clear the denominators might be linear, or it might be some polynomial equation. Whatever type of equation you get, you will solve using an appropriate method. Then you have to check your answers. And when I say check, I don't mean just check to make sure that you've gone through the process of solving correctly, but to check to make sure that your answer agrees with the domain. So in this video, we'll take a look at the first two examples that you see on the slide. Let's go to the first one. So here you see you have variables in the denominator. We have p. So the first thing that we will do is check the domain. We're looking for all values that would make any denominator 0, and then we're going to exclude them. So we can start by saying that the domain is all reals except, and then we'll just make a list of the values that are no good. There are lots of different ways that you can express the domain using interval notation or set builder notation. We're just going to write it in words right now because it's just a little reminder for us to think about at the end. So looking at the denominators that contain a variable, I have p and 4p. You could always set and write yourself a little equation to help you to find out the value that would make that 0. So p equals 0 is already given. We have one value that we're excluding, 0 itself. And then even if I look at the other denominator, set that equal to 0, and I solve that equation, I also get p equals 0. So the only value that we are excluding is 0 itself. So all reals except 0. So we'll use that to check our solution, make sure our solution does not end up being 0. All right, so now we're going to the process of solving. We're going to use the least common denominator to solve this equation. Looking at the denominators that I have, p, 4p, and 8, the least common denominator would be 8p. So I'm going to use that and multiply every single term, or both sides of my equation, by 8p. So multiplying this side by 8p, multiplying the other side by 8p. So multiplying both sides of the equation by the same value, so I'm still holding that property of equality, and I do know that p can't be 0 from my domain, so I'm not clearing out this equation. When we do multiply by 8p, we're really multiplying the numerators of all the fractions. So multiplying the first 8p times 8 over p gives you 64p over p. That can be simplified. I'll do that in the next step. Then we have 8p times 1 over 4p. That gives us 8p over 4p equals the other side, multiplying the numerator, 88p over 8. Now the whole point is to write an equation where we can simplify and get rid of all those denominators. And you'll see that all of my denominators will cancel out. So just go ahead and do that. So p divided by p is 1. 8 divided by 4 is 2. So this side gives me 64 plus 2 equals, and here I can divide 88 by 8 and get 11p. So you'll have some sort of equation. You have to decide what type of equation that is and what method you need to use to solve. This is a linear equation. The degree is 1, p to the first power, which means I want to isolate p. So 64 plus 2 is 66 equals 11p. Divide by 11, and I have 6 equals p. So now I have my solution. I want to check my solution with the domain, make sure that it's not one of the values that I need to exclude, that's not going to make my equation undefined, and it isn't. So 6 is not equal to 0, which is good. And then the second check is the optional one. That means, just plug in to make sure you've done your steps correctly. If I plug in 6 for the values of p that we see here and go through the order of operations, the left side should equal the right side. So I'll leave that part of the check to you. So here we have one solution. I'll just write it in roster form, the set of 6. Going back to our second example here, number 2, here we have a very specific type of rational equation. This type of rational equation is called a proportion because we have one fraction on either side of the equal sign. So a fraction equals a fraction. So these types of rational equations have a kind of a shortcut method of using the LCD to clear them out, and that's a method of cross multiplying, which you may have seen before. But we're still going to first check the domain just to make sure that the solutions we get don't make either of our expressions undefined. All right, so here we are. So checking the domain first, I want to look at the denominators and see what values would make them undefined, and then I'll exclude those. So my domain will be all reals, except, and I'm just going to find out what those values that I'm excluding are. So I'll do that by taking each denominator, setting it equal to 0. So if x plus 3 is equal to 0, then x is equal to -3, which means I want to exclude -3 from the domain. The second denominator, 2x plus 3 equals 0. If I subtract 3, I have 2x equals -3, and then divide by 2, I have x equals -3 halves. So I'm also excluding -3 halves from the domain. So x can be any other value except for -3 or -3 halves. So if I get one of those as a solution, I'll have to get rid of it. I'll have to throw it out. All right, so we are still technically using the process of finding the least common denominator, but because we have one fraction on either side of the equal sign, when we multiply by that least common denominator, what we actually end up doing is multiplying the left-hand side by the denominator on the right, and then the right-hand side by the denominator on the left. So as a shortcut, we can go through a process called cross-multiplying, which you might have done before if you had a proportion with just a single monomial, a single real number in each of the positions, but now we're doing it with polynomials. All right, so writing that out first, I have 2x plus 1. That binomial needs to multiply the binomial 2x plus 3, and I'm setting that equal to the product of x plus 3 times 4 times x minus 1. I need to have parentheses around those binomials because I'll have to use the product of polynomials to actually do that multiplication. All right, so multiplying the left-hand side, 2x times 2x is 4x squared. The outside gives me 6x. The inside is 2x, so that's 8x. And the last 1 times 3 is 3. on the other side. Let's see. So I'm going to multiply the two binomials first, and then I'll distribute that 4 after. So I'm multiplying x times x, which is x squared. The outside is negative 1x. The inside is positive 3x, so that's positive 2x. And the last product is negative 3. So I multiply the two binomials together first, and then I'm just going to distribute the 4. You can multiply in any order, right? There are just 3 things that are being multiplied. Multiplication is commutative and associative, so you can swap things around and you can change the grouping. Now I'll distribute that 4. So that's 4x squared plus 8x minus 12. This side is still the same, 4x squared plus 8x plus 3. All right, so I want to go ahead and think about what type of equation I have. I see that it's a degree 2 equation, a polynomial equation, so I'll begin by trying to get all of my terms on the same side. However, in this case, I see that the x squared terms cancel out. I have negative 4x on both sides. Here I have 8x plus 3 equals 8x minus 12. So by trying to isolate my variable 8x, I will see that the x's cancel, and I'm left with 3 equals negative 12. Oops, which you can't see on your screen. All right, so in this case, I have a statement that is false. The variable disappears, but I'm left with a false statement. 3 is not equal to negative 12. So this means that I have no solutions for the empty set. So I can write the empty set in that set builder notation like that. In the next video, you'll see some more examples.